Very good morning. This is R. Premananda, Assistant Professor, Government Engineering College, Avia. This video lecture is regarding the subject Signals and Systems, subject code 18EC45 for the students of 4th semester. I am going to present in this session regarding the Model 3 and of the session 7, which indicates the continuous time periodic signal or Fourier series. A periodic continuous time signal x of t can be expressed as x of t is equal to summation of minus infinite to plus infinite x of k to the power j k omega naught t, where x of k is 1 by t, the integral of x of t to the power of minus j k omega naught double naught t dt with respect to dt, where x of t as the fundamental period t and a fundamental frequency wt or double naught, which is equal to 2 pi by t or radians per second. Equation 3.7 and equation 3.72. In equation, x of k are known as Fourier series of x of t. Fourier series of x of t, and equation 3.7.1 is known as synthesis equation. And equation 3.7.2 is known as analysis equation. Okay. We say that x of t and x of k forms a Fourier series pair and is denoted by the symbolic representation, where x of t is the continuous time, x of t is time domain representation, and x of k is the frequency domain representation. Okay. We have the different properties of Fourier series. Actually, this is a continuous time periodic signal Fourier series. Since it is also called as Fourier series. In this section, we discuss the different properties of Fourier series. They are linearity, time shift, frequency shift, scaling, time differentiation, convolution, modulation, Percival theorem, and symmetry. See, in previous discussion, that is model session 3.5, there we discussed about the DTFS, discrete time Fourier series. Okay, that is DTFS. Now this is CTFS, but we simply call it as FS, continuous time Fourier series or Fourier series. This DTFS and CTFS are for the periodic signals only. For aperiodic signals, we will have the transformation, Fourier transformation, that is DTFT, discrete time Fourier transform, or simply FT, the Fourier transformation. Okay. Next, we will study the properties one by one. First, we go to the linearity property. If you say that x of t can be represented x of k, then y of t can be represented as y of k. Then z of t, a times x of t plus b times y of t can be converted into a times x of k plus b times the y of k, where x of t are in time domain and x of k are in frequency domain. A and b are the constants. Okay, they are linear. If we satisfy this condition, we say that the given property, linearity property, have been satisfied. So in both cases, we say that since this is the periodic signal, we have the period t is equal to 2 pi by double naught. We start the proof. We know that x of k can be written as 1 by synthesis equation can be written as shown here, x of k. Here we have written the equation Fourier series. X of k integration, that is called as analysis equation. Inverse equation we call it as synthesis equation, and direct Fourier series equation is called as analysis equation. Similarly, we represent y of k in terms of analysis equation as shown. Similar, both only that x and y has changed. Similarly, z of k, because we need to find that z of k. So z of k will have that equation as shown here. And we will apply the z of t. We apply what is z of t? Z of t is nothing but a times the x of t plus b times the y of t. We have to convert, we have to prove that this and both are same. Whereas this is in time domain and this z of k is in the frequency domain. And even in frequency domain, it holds the property of the linearity, we have to prove it. So, as this is the integration and this is summation, we can split these two. Where in first part we'll have completely with respect to x of t, and second part we'll have that with respect to y of t. Okay, and everything is shifted. Okay. and solving this, a is the constant with a function of dt. So is a is the constant and here b is the constant. So after at the point, this entire first term apart from the a is nothing but it is x of k, whereas the entire this term, the second term apart from b is the y of k. So z of k is equal to a times x of k plus b times the y of k. Hence it proves the linearity property. Time shift. If x of t, as you know that applying the Fourier series of Fourier series form, you get x of k, then w of t is equal to, so you have given the name w of t for x of t minus t naught. What is this t minus t naught? This is the shifted version of the x of t. If you apply this to the Fourier series, we will get this as w of k is equal to e to the power of minus j k naught k omega naught t naught x of k. Okay, this is the time shifted frequency shift. In time shift, the time shifted signal applied to the Fourier series, we get the frequency shifted component. So we have that proof that I will take the what is x of k, I will write another equation for the x of k and the equation for the w of k. We will express w of t in terms of x of t minus t naught. What is w of t? It is x of t minus t naught. We applied here. Then we will put t minus t naught is equal to m. If you put t minus t naught is equal to m, then t will become m plus t naught. Wherever t minus t naught is there, put m. Wherever t is there, put t naught plus m. And since it differential also be converted instead of dt, now we can express in terms of the dm. Okay. Then here, see here the integration with respect to dm. Apart from m, everything is constant. Which all possible, we will take outside the integration. So e to the power of minus j k w naught t naught is the constant which has been taken outside. So that remaining is x of m e to the power of minus j k omega naught m. So this is nothing but this is x of k. So w of k is equal to e to the power of minus j k omega w naught t naught into x of k. So in time shift, in time domain, if it is a time shift, in Fourier series, this will be our, in frequency domain, there will be a frequency shift. So here in time domain, if it is a frequency shift, okay, in the time domain itself is the frequency shift. Okay, we have to get the e to the power j omega naught e to k naught e to the naught. X of t can be converted in terms of w of k equal to x of k minus k. Okay, where x of k I will represent that. Okay, instead of w of t, we will write all this term e to the power of j omega naught k naught t into x of t. So with this, here everything is a function of dt. So we'll take common here minus j omega naught t is common on both exponential. So we'll take that, we'll get the e to the power of minus j k minus k naught omega naught t. See, if in this e to the power of minus j, if it is k is there, we will get x of k. Here is k minus k naught is there. So this will be x of k minus k naught. Means pre-shift in the frequency. The scaling property. Okay, if x of t Fourier series applied, Fourier series, you get x of k. Then w of t, if you apply x of at, we get w of k is equal to x of k. If x of t is periodic, then w of t is equal to z of at is also periodic. If x of t is fundamental period t, then z of t is equal to z of at as a fundamental period t by a. Alternatively, if the fundamental frequency of x of t is also w naught, then the fundamental frequency of z of t is equal to x of at is also a omega naught t. Okay. Okay. W of k, t here the time period will be t by a. You put at is equal to m, then dt is equal to a by t. So that z of k is equal to x of k. Therefore, Fourier coefficients of x of t and x of at are identified, but the harmonic spacing from w naught to a w naught. Time differentiation. Here, differentiating the input time domain signal x of t. Apply to the Fourier transform, we will get this as j k omega naught x of k. Okay, we will take that the synthesis equation, that is inverse Fourier series equation, where you get the time domain signal as an output. So x of t is equal to summation of minus infinite to plus infinite x of k e to the power of j k 1. This is the synthesis equation. Differentiating both with respect to t, we get this as d of k as shown here. And changing the order of summation and the differentiation can be written like this. Okay, this is nothing but at the final result we will get the differentiation x of t of dt is equal to j k omega naught into x of k. Okay. Convolution. In time domain, if it is convolution, in frequency domain that will be multiplication, or we can call it as a modulation. In this case, both x and y of t are assumed to be periodic with the, see, throughout this session, we are discussing with respect to periodic signal only, so that capital T is equal to 2 pi by double naught. X of k written in terms of analysis equation, y of k and z of k. So z of k is we are represent z of t in place of z of t, we call that x of t convolved with the y of t. And the convolution of this x of t convolved with y of t is given by the integration of x of L y of t minus L. This is the integration form of the convolution of the x of t and the y of t. So changing the order of integration, sorry, it has been named as differentiation, changing the order of integration, we get that, I can write as it is. Put here, we got t minus L, put t minus L is equal to m. See, at last, actually, this property we have to prove. These all property holds good by the Fourier series. We are proving that. Okay, put t minus L is equal to m, then dt will become dm. Now replace all t minus L with respect to m and t with respect to m plus L. See, if you eliminate entire small t term, a time domain signal. So here t minus L is there, so m will come. Yes, t is there, so m plus will come. Okay, here dt was there, so it will come dm. Means everything t is represented in terms of m. Okay. Now at the end we will write this as shown here. See, this is nothing but, this is also an analysis equation. This is an analysis equation, but instead of k, here we got in terms of L. Okay, instead of k, we have instead of t, we are getting in terms of L. So this is nothing but this is x of k. This is x of k. So only this term is there. So this is t times the x of k. The same equation, but here in terms of m is there. So this is also x of k. Okay, this is also x of k. So but t is not here. 1 by t is not here. So the t times the x of y of k. So this is t times the x of k, whereas this is t times the y of k. So we'll get this t times x as shown here. One t will be eliminated, and finally we'll get z of k is equal to t times x of k and y of k. Whatever the convolution in time domain, now in frequency domain it is an multiplication. In frequency domain, that is an multiplication. Okay. Modulation, or you can call it as multiplication. In time domain, if it is a modulation or multiplication, whereas in frequency domain it will become a convolution. So writing the synthesis analysis equation for x of k, y of k and z of k. Z of k is equal to integration of z of t. Applying z of t is x of t to y of t. Applying that, the whatever z of t we have got here, applying, then, and we know that the synthesis equation x of t is equal to x of L into e to the power of j k omega naught t. Okay, one, so you got x of t and y of t, both are in time domain. For this x of t, we will write the synthesis equation or inverse Fourier transform equation in the next step. Okay, so that after changing the order of summation and integration, we can write this as a summation of L minus infinite plus infinite x of L. Whatever the t terms, all taking one side, So 1 by t times the integration with respect to t, integration with respect to t, that is y of t e to the power of minus j. See, here also you got the exponential with respect to e, here also with exponential with respect to t, e. Here j omega wt double naught and t are common. Taking that e to the power of j omega naught t common, will remain this as k minus l. So e to the power of minus j k minus l omega naught t dt. Okay, and this term we can, this is nothing but an analysis equation or Fourier series equation with k minus l. As there e to the power of k minus l is there, then it will also become y of k minus l. Okay, this is nothing but integration, summation of minus infinite to plus infinite with respect to l. X of l y of k minus l is nothing but the convolution, differential time convolution. Okay, so this can be written as discrete time convolution. This is x of l convolved with the y of k. This means that multiplication in time domain is convolution in the frequency domain. Next, we are going to discuss about the Parseval theorem. What Parseval theorem says? The energy signal in time domain is equal to the energy signal in the frequency domain. That is 1 by t times the integration of x of t square with respect to dt is equal to summation of minus infinite plus infinite x of k square, where x of k is the coefficients of the Fourier series, x of t's are the coefficients of the time domain series. So we will take the average power equation, that is p is equal to 1 upon t times the integration of x of t square. That is, see, this x of t can be written as x of t into x conjugate of t. This x conjugate of t, that is this is nothing but inverse Fourier series. I will represent that inverse Fourier series. See, as it is inverse Fourier series, the conjugate is there, this term will be e to the power of minus j, it will come. Actually, in actual synthesis equation, e to the power of plus j will be there. Because of conjugation, you will get the minus j. So applying this, okay, x of k, and changing the order of summation and integration, we will write this equation as shown here. Okay, see, this x of t to the power of minus j common is nothing but x of k, this capital X of k. See, capital conjugate of x of k and x of k, this is nothing but modulation of x of k square or absolute value of x of k square. This means that we have proved that the integration of square of time domain signal is equal to the summation of square of frequency domain coefficients for all k is equal to 0 to n. Next is symmetric property, x of t. So it is n means the discrete time, we have to represent x of t with applying Fourier series with respect to omega double naught. X of it in terms of x of k in terms of frequency domain means we'll get the if x of t is real, then x conjugate of k is equal to x of minus k. If x of t is real and even, then imaginary of x of k is equal to 0. If x of t is real and odd, then the real value of x of k is equal to 0. This is our LMS team, and if any questions, please comment it personally to that team. We will try to solve this problem.